In chapter 2.6, we begin studying rational functions. So, what is a rational function? So far in this chapter, we've talked about a lot of our different quadratics. Here, we're going to study the difference between rational functions and how we are going to sketch their graphs. So, a rational function is a quotient of polynomial functions. It can be written in the form f of x is equal to n of x divided by d of x, where n of x and d of x are polynomials, and d of x is not the zero polynomial. In other words, I have a polynomial divided by another polynomial. That is our definition of a rational function. A polynomial in the numerator and a polynomial in the denominator. In this section, we will learn how to sketch graphs of rational functions. As with all sketches, it will be important to determine the domain of the function, the intercepts, that's x and y, and the end behavior as well. What does the graph do as the function goes to the left? And what does the graph do as the function goes to the right? The domain of a rational function is all the real values of x that do not make the denominator equal 0. This means, in a lot of these cases, we are going to want to factor the numerator and also factor the denominator. Notice that if the denominator is equal to 0, the function will be undefined. Values of x that are not in the domain will result in either holes or vertical asymptotes in the graph. So anywhere where your function is undefined, you have one of two options. You will either have a hole or a vertical asymptote for these rational functions. And then, finally, to determine the end behavior, we will look at what happens to f of x as x goes to positive infinity and as x goes to negative infinity. Again, what happens as the graph goes to the right and as the graph goes to the left. So let's do a little exploring here. Let's start off with a function. We have graph the function f of x is equal to 1 divided by x. And this is an example of a pretty basic rational function. I've got a polynomial in the numerator. Notice it's just a constant function, actually, one term, divided by a polynomial in the denominator. And this is just a basic linear function in the denominator. So what is our domain? Well, as you guys know, the denominator of a fraction cannot equal 0. Therefore, our domain is going to be all real numbers except for x cannot equal 0. If we plug in 0 into the function is undefined. So let's talk about what happens near x equals 0. Well, let's create a table of values. Notice, here I have some different x values, and these x values are getting closer and closer and closer to 0, but notice that they are all to the left of 0. If we were to plug in these values into our function f of x, I would have 1 divided by negative 1. Well, that gives me negative 1. If I plug in negative 1 half, 1 divided by negative 1 half, that gives me negative 2. 1 divided by negative 1/10, that gives me negative 10. 1 divided by negative 100th, that gives me negative 100. 1 divided by negative 1,000 gives me negative 1,000. And so what's happening here? As my x values get closer and closer to 0, as we approach 0 from the left, that's what this little minus sign notes, all right? As our x values get closer to 0 from the left, our y values get closer and closer to negative infinity. As the x values approach 0 from the left, the y values approach negative infinity. And that means that our graph is going to do something like this. As the x values get closer to 0, the y values go down to negative infinity. All right. Let's see what happens as x approaches 0, but from the right. So here I have a bunch of different x values, and each one of these is to the right of x equals 0. Well, if I plug in 1 into the function, 1 divided by 1, that gives me 1. If I plug in 1 half into the function, 1 divided by 1 half gives me 2. I plug in 1/10, 1 divided by 1/10, that gives me 10. I plug in 1/100th, that gives me 100 out. I plug in 1/1000th, 1 divided by 1/1000th gives me 1000. And so what is happening to our function here? As my x values get closer and closer to 0 from the right of 0, the y values get closer and closer to infinity. All right, as the x values approach 0 from the right, as we approach 0 from the right, the y values approach positive infinity. And so that means on our graph, as the x values get closer and closer to 0 from the right, the y values have to go up and up and up. Okay. All right, so a little bit of analyzation of our graph there. Let's now talk about the end behavior. All right, what happens as x approaches negative infinity? This means as our graph goes to the left. As our graph goes to the left, what does it do? Well, think about what would happen if we were trying to evaluate f of negative infinity. In other words, we're plugging in an infinitely large negative value into the function. I have 1 divided by an infinitely large negative number. Well, if I take any real number and try to divide it up an infinite number of times, I am going to get 0. This tells me that as the x values approach negative infinity, the y values approach positive infinity. But in this case, they'll also be negative. Notice I have a positive divided by a negative. So what does that mean graphically? As my x values go to the left, the y values have to get closer and closer to 0. All right, our graph would look something like this. Okay, what happens as x approaches positive infinity? Imagine trying to plug in infinity into our function. We would have 1 divided by an infinitely large number. And 1 divided by an infinitely large number, well, that is also going to equal 0. As the x values approach infinity, the y values approach 0, and in this particular case, they are going to be positive. Notice that a positive divided by a positive is a positive number. So this says, as my graph goes to the right, the y values have to get closer and closer to 0, but they are going to be positive. What would that look like on the graph? All right, that portion right here. So that's all of our behavior there. What about our intercepts? How do we go about finding x-intercepts? Well, to find x-intercepts, you set your equation equal to 0. And notice, is this equation ever going to equal 0? No. The only time a fraction ever equals 0 is if the numerator is 0, and the numerator of our function is always going to be 1. Therefore, there are no x-intercepts. How do we find y-intercepts? To find y-intercepts, we plug in 0 for x. Well, what happens when we plug in 0 for x into our function? The function is undefined, and therefore there is no y-intercept. The function is undefined at x equals 0, so if I have no intercepts in this graph, imagine what our final graph is going to look like. What's our final sketch? Well, we can just kind of connect these curves, these portion of these curves, and here we end up with the graph of f of x is equal to 1 over x. Now, a few important things to take away from the process that we just went through. Okay, vertical and horizontal asymptotes, you might notice, is the title of this slide. The behavior of our graph near x equals 0 in this case results in what is called a vertical asymptote. The line x equals a is a vertical asymptote of the graph of f if f of x goes to or approaches positive or negative infinity as x approaches a, either from the right or left. The function is said to increase or decrease without bound as x approaches a. And notice, if you look at this particular graph, here we have a vertical asymptote at x equals 0. All right. As we approach 0 from the right-hand side, the function goes up towards positive infinity. As we approach 0 from the left-hand side, the function goes down towards negative infinity. Anytime your graph goes to positive or negative infinity as x approaches some real number, in this case as x approaches 0, you are going to have a vertical asymptote. Now, the behavior of our graph as x approaches positive and negative infinity, that's the end behavior, results in a horizontal asymptote. Okay, the line y equals b is a horizontal asymptote of the graph of f if f of x approaches b as x goes to positive or negative infinity. So in this case, what do the y values get closer and closer to as x goes to positive infinity? They get closer and closer to 0. What do the y values get closer and closer to as x goes to negative infinity? They get closer and closer to 0. Therefore, we have a horizontal asymptote at y equals 0. All right, so notice vertical asymptotes and horizontal asymptotes are equations of lines, and make sure you write them as such. Okay, here we have x is equal to 0. That is a vertical line. Here we have y is equal to 0. That is a horizontal line. And there we have our definitions of our vertical and horizontal asymptotes. All right, we'll talk more about vertical and horizontal asymptotes coming up, but there is your introduction.